We're now going to look at the relationship between the cell potential, the Gibbs free energy, and the equilibrium constant. And so we already know for a spontaneous reaction that's going in the forward direction that our delta G has to be negative, our cell potential has to be positive, and the equilibrium constant has to be greater than 1, so it proceeds towards the products. And so we have relationships that relate these different values. If we want to look back at the last chapter, we had a relationship that related Gibbs free energy to our equilibrium constant with the ideal gas constant and temperature. We have a similar relationship that relates Gibbs free energy to our cell potential that has to do with the number of moles of electrons and Faraday's constant. And so we've got N, the number of electrons, Faraday's constant, which is 96,485 coulombs per mole of electrons. And so we are going to look at now is the relationship between the cell potential and our equilibrium constant. So if we want to find that relationship, we're going to set the other two relationships that we just talked about equal to each other, and then solve for the cell potential under standard conditions, because remember that little degree sign means that we're under standard conditions. And rearranging our equation, we end up with the ideal gas constant times temperature divided by number of moles of electrons times Faraday's constant, all of that times the natural log of our equilibrium constant. So if we substitute in all of those constant values and we use a temperature at standard conditions, convert the natural log to log, we come up with a new equation that is the cell potential under standard conditions is equal to 0.0592 volts over the number of electrons times the log of K. What if we want to measure the cell potential under conditions that are not standard? Well, in this case, we're not going to be exactly at equilibrium, and so we've replaced the K value with Q. We're still looking at a temperature of 25 degrees Celsius, and so we can substitute the RT divided by Faraday's constant, and we end up with that 0.0592 volts again. N is the number of electrons that are being transferred in our chemical reaction, and we're looking at the standard cell potential minus that new value. And this can help us find the cell potential under non-standard conditions. This is known as the Nernst equation, and it helps us determine that cell potential. This is a very important equation, and we'll look at a couple of examples of how to use it. So let's calculate our Ecell at 25 degrees Celsius for the following chemical reaction. So we've got our conditions. We've got the concentration of our copper 2+. We've got our permanganate concentration and the concentration of our acid. So our copper to our copper 2+ is the oxidation. The reduction is our permanganate to manganese 4 oxide. Now, how do we end up with our overall reaction that we already have written up above? Well, we need to make sure that our electrons balance. So in order to make sure our electrons balance, we're going to have to multiply our copper half reaction by 3 and our permanganate half reaction by 2 so that our electrons will cancel and equal our overall chemical reaction. Now, how about calculating our Ecell? Now, normally and previously, we said that it is the reduction minus the oxidation. But in this case, because we have one written as oxidation and one written as reduction, they're not both reduction half reactions, we actually add the two together. So our Ecell under standard conditions is going to be the 1.68 volts plus our negative 0.34 volts. Now, if we were subtracting them, we would have to reverse the reaction for the oxidation, and we would end up with the same value. Our overall is going to be a positive 1.34 volts. So now let's calculate our Ecell. Because we're not under standard conditions, we're going to use our Nernst equation. Our Ecell is equal to the standard cell potential minus 0.0592 volts over the number of electrons times the log of Q. So in this case, our Q is going to be products over reactants. Remember, we leave any solids or liquids out, so our manganese 4 oxide is not in our Q, neither is the water, and so we are going to get our copper 2 plus raised to the 3rd power because we have a coefficient of 3 divided by, remember, our copper solid is going to be left out, so we have our permanganate squared because of the coefficient of 2 times the H plus concentration to the power of 8. And so we can substitute our values in. Our standard cell potential, that's the positive 1.34 volts minus 0.0592 volts divided by the number of electrons transferred. Remember, we had to multiply, so we have 6 electrons transferred in this reaction. Times the log of our copper concentration that was given to us to the 3rd power, our permanganate concentration squared, and our acid concentration to the 8th. And if we solve this equation, we get 1.41 volts for our answer under non-standard conditions. Here's a practice for you to try to calculate the Ecell using the Nernst equation for the overall reaction of iodate in acidic solution plus iodide, giving us iodine plus water. So our initial our concentrations of all of our reactants are 0.1 molar. The Nernst equation and how to calculate the standard potential for the cell are here for you. And our 2 half reactions for this overall reaction. Please try to calculate the cell potential under non-standard conditions. Okay, so let's start by calculating our overall cell potential. So if we add our two cell potentials together, our oxidation cell potential plus our reduction cell potential, we end up with our overall cell potential of 0.66 volts. Okay, we are also going to need to know the number of electrons, and so from our two half reactions, we've got 2 electrons and 5 electrons. So our oxidation, we would have to multiply by 5. Our reduction, we would have to multiply by 2. And so we would have overall 10 electrons for our equation. So let's plug this into our Nernst equation in order to find our cell potential. So our standard potential is what we calculated for the cell under standard conditions, minus 0.0592 volts over 10 electrons times the log of products over reactants. And in this case, our products are both not included in our equilibrium constant expression because they are both liquid and solid. So we're going to have 1 over our iodate concentration, which is 0.1 molar. And that's going to be squared from our coefficient. Our acid concentration, which again is 0.1 molar. And that is going to be raised to the 12th power times our iodine, or iodide, I-, which is also 0.1 molar, and that is going to be raised to the 10th power. Right? If we solve this equation, okay, the 0.1 squared, 0.1 to the 12th, 0.1 to the 10th, that is 0.1 to the 24th. 1 over that is 10 to the negative 24th. So we can take the log of 1 times 10 to the negative 24th times 0.0592 divided by 10. And we end up an Ecell of 0.52 volts for this overall cell under these conditions. Okay, if we vary the concentration of our solutions, in this case we're looking at 2 copper half reactions or half cells under the same conditions, we should have a potential of nearly 0. The electrons are not going to want to flow one direction or the other. However, if we change the concentration, so here we still, on this side, we still have 2 copper half reactions, but now our concentration is different between them. So one has a solution of 0.1 molar, one has a solution of 2 molar. And so we're going to try and reach an equilibrium by decreasing the concentration of the solution by removing ions. So solution becomes less concentrated with the flow of electrons. So we're going to be plating copper out onto that electrode. And then the other less concentrated cell is going to become more concentrated by allowing more of the Cu2 plus to form. And so we do get a difference in voltage when our concentrations are different. And you'll be looking more at this in the electrochemical lab. So why do we care? Why do we care about all this electrochemistry? The reason that we care is because this is what runs our world. Batteries are using redox reactions in order to create voltages that can be used to power the tools of your life. There's lots of different types of batteries. So nickel cadmium, nickel metal hydride, lithium ion, which lithium ion is probably the most common now. And the reason for this is because it has a much higher energy density. So we can get more power with less weight because lithium on the periodic table has a very low mass. Another type is lead storage, and these are what get used in automobiles most frequently. Another way that we can produce energy through redox reactions is using fuel cells. And unlike batteries, which have a fixed amount of reactants, we can constantly add in hydrogen and oxygen. And as long as those reactants are present, the fuel cell will continue to produce electricity, so we don't have to worry about it running down. We do use the anode and cathode. Both are platinum-coated metal, and this still has to be done in a basic solution. So at the anode, what is happening is we are taking hydrogen gas in a basic solution, and it produces water and our electrons. The cathode reaction is oxygen plus water, and we add those electrons back in to get our hydroxide. So our overall chemical reaction is 2 hydrogen plus oxygen gives us 2 water molecules. So our water would cancel, our hydroxides would cancel, and our overall reaction would produce water. These are interesting in the fact that, or they're looked at quite a lot because this would be a very environmentally friendly way to produce electricity. One hazard is storing hydrogen gas in a safe, economical way.